Anin, Bojo, Sarah Hazel Dishnikaz, Nibizing Donjaba. Hello and welcome. My name is Sarah Hazel and I'm from Nipissing First Nation. I am also the project manager for the Canadian Archaeological Association's Working Group on Unmarked Graves. Today I'm going to be talking to you about recommended data processing and visualization procedures for ground penetrating radar. Before we get started, I'd like to draw your attention to our online resources and specifically our comprehensive guides on investigation planning and remote sensing applications, which you can access by this link on the slide. Unmarked graves investigations can bring up distressing content, and it is important to take care of yourself mentally and emotionally while doing this work. Please make sure you have health supports in place, or you can call one of the numbers on the slide if you are feeling triggered and you can speak to a health professional. And I'll just leave this up for a moment in case you'd like to write one of these numbers down. GPR generates data on the amplitude or strengths of reflections in the subsurface within a chosen study area. Turning these data into usable information is a complex process that will likely involve technical experts employing software to extract useful data from noise and then interpreting the results. While complicated, the basic workflow and principles of data processing and visualization can be understood by anyone. And this guide is an effort to make sure this middle stage of GPR projects is less complicated. Often processing is conducted after data collection is complete, but it is also advisable to process and visualize a small portion of the data as a pilot step in a GPR project or even during data collection, as this will allow for early identification and prevention of problems in the data collection process. In a survey, GPR data is collected in 2D vertical reflection profiles known as radargrams. Once the data has been collected, the first step is to transfer the data to a computer on which the processing and visualization software has been installed. There are various pieces of software that will do this job, and each performs similarly in a general sense. Typically, the proprietary software of the machine's manufacturer is used. However, there are third-party or open-source software packages that will work with data generated by many different types of GPR machines. Consultants and researchers likely already have a machine and software workflow established. Usually the transfer is as simple as connecting the machine's data collector to a USB drive and then transferring the data to a computer via the USB device. The following steps may be in a different order depending on the specific software you are using. However, regardless of the order, each step is an important part of the overall processing and visualization procedure. Once the data is uploaded to the computer, the second step is to ensure that the software understands how the data was collected. This includes 1. Inputting the length of each line or transect and where they begin and end. 2. Transferring system information and settings that describe how the data was collected, for example, the density of scans and the depth that was scanned, though this information is often read automatically. Number 3, how many profiles were collected. And 4, any other relevant grid or survey information. For example, if you've removed any profiles that include errors or indicating lines that were shorter or longer due to objects in the machine's path. These are all critical to ensure accurate results. Different software packages have different ways to accomplish this, but for software that is paired with the machine, that is from the same manufacturer, this step can be relatively simple. The third step is to process the data. This usually involves several standard steps initially, including finding time zero. This means locating the first usable data from when the radar wave hits the ground surface after being emitted from the machine. After finding time zero, the data from above the ground surface can be removed. Following this correction, usually a gain model is applied to the data. Since waves lose energy as they continue deeper into the ground, the signal from greater depths has to be boosted or gained. Gain can be automatically applied by the software, or it can be a user-specified amount of boost for different depths that need more or less gain to highlight features for interpretation. It should be noted that this often takes some experimenting. The fourth step is the application of filters. Filters are applied to the data to reduce noise that can obscure collected data and enhance visualized features. There are various filters and transformation processes that accomplish this, each of which can greatly aid interpretation. Generally, it is prudent to apply as little filtering as necessary to avoid creating effects that could be misinterpreted as targets of interest. Commonly used filters include background removal, which removes horizontal lines in the data, a bandpass filter, which removes data frequencies below and above the useful range of the GPR antenna, and a Hilbert transformation, which transforms wave reflections from both negative and positive responses to just positive responses. A process called migration is also often applied at this point, which turns the convex-shaped reflections, or hyperbolas, that discrete objects make into more of a focused signal. It is important to note that the speed of the wave in the ground can be measured by analyzing the shape of these convex reflections, an important process that experienced software users can and should do to accurately estimate the depth of the objects in the ground. In cases when the GPR data is not collected on flat ground, correcting the data is typically a necessary step. Correcting for topography ensures the most accurate positioning of the GPR reflections and amplitudes prior to interpretation. By the end of these steps, the software should have produced relatively clean visualizations of the GPR profiles or radargrams that are ready for interpretation. Most GPR software also offers the capacity to see GPR data from a bird's eye view at any given depth, known as amplitude maps or time slices. While GPR is collected in profiles, these can be lined up side by side and stitched together to form a block. Software can then slice this block horizontally into GPR maps for specific depths or thicknesses. Slicing to get these views is often best accomplished with data collected in grids, in rectangular-shaped areas of the ground surface, but they can also be generated from other less regularly spaced types of data or GPS-driven data collection sets. These amplitude maps or time slices highlight strong reflections at specific places within the grid, often called anomalies or targets, which can correspond to specific features of interest. By default, red areas of the map show unusually high reflections, while blue areas typically show average background reflection strength, and scaled colors show reflection strengths in between the background average lows and the high peaks. The various software packages have different ways of creating slices, and there can be quite a few user decisions to be made when generating them. Therefore, this step is best undertaken by someone with experience with the software being used. Interpreting amplitude maps has several advantages. The reflection patterns are presented in a relatively intuitive way. One can inspect surface reflection patterns at any depth, and one can usually scroll up and down the slice depths to get a picture of subsurface features at various depths. It should also be kept in mind that slices are an interpretation, meaning they are based on a smoothed and transformed dataset. Using both GPR radargrams and these depth maps to understand any anomaly or feature is vital to the interpretation process. Many GPR visualization software programs can combine these two forms of data to create impressive 3D visualizations of the subsurface. These tools can be used to create impactful and intuitive representations of subsurface features, including graves, and the soil layers in which they are embedded. The steps involved in processing GPR data are technically complex, but the basic principles are readily understandable. Not all communities that undertake or commission GPR surveys will complete this middle stage of the work on their own. The goal of this brief overview is to provide enough information so that communities can work with GPR specialists to achieve the results they want and need for their communities. It is important to recognize that the various contexts in which GPR is applied can present some challenges, but overall many steps in the process are the same. The processing and visualization stage will likely involve significant trial and error to best represent the features most of interest. There are no cookie-cutter ways to do each of these steps, but the overall sequence of steps and goals is similar in most cases. GPR software packages often have recipes of predetermined processes and filters that can be applied to data. It is important to recognize that these stock recipes may not be appropriate for your data, especially not without careful exploration and assessment of the results relative to other recipes or single transformations. Most advanced researchers create their own recipe based on the specific site conditions, and we strongly recommend this approach. Once the GPR data has been processed and visualized, the third stage of the GPR project can be started: interpretation. Miigwech, thank you for joining me for this module on recommended data processing and visualization procedures for ground penetrating radar. Please visit our website for more resources, and take care.